Thursday, 6:42 p.m. A commuter boards a hot bus with 9% battery, watching distant wind turbines turn. Every new machine needs a new material. DFT was the bottleneck, because solving electrons exactly does not scale. Software feels fast. Hardware waits for conductors, cathodes, catalysts, and crystals that work. Density functional theory, or DFT, estimates electron behavior, like calculating a crowd from its density, instead of tracking everyone. For large atomic systems, even this shortcut becomes computationally crushing. The commuter feels the result: slower batteries, wasted wind, hardware constrained by matter. That frustration gave Google DeepMind a target. Its Graph Networks for Materials Exploration System, GNoME, represents atoms as connected points, then predicts which arrangements remain stable. It does not discard quantum physics. It learns from physics calculations, allowing researchers to screen candidates before spending laboratory time. The engineering question is precise. Can a learned electron map narrow millions of structures without confusing mathematical stability with manufacturable matter? Only the laboratory can decide. The delay feels absurd because tiny atoms share one coupled electron system. The Schrödinger equation describes its possible states. Solving it exactly means tracking combinations that multiply explosively with every added atom. DFT avoids that wall by calculating electron density, the crowd's shape, not every individual path. Its cone-sham procedure updates that density until input and output agree, like correcting a map until every road connects. Useful, accurate, still expensive. Every candidate demands another loop. Millions become a supercomputer queue. What changed was not physics, but representation. That is when the constraint became training data. That data lets graph neural networks learn local atomic relationships, like reading a neighborhood from which atoms touch. Neural SCF goes deeper. It learns the cone-sham density map and imitates repeated self-correction instead of restarting each calculation from zero. Related molecular language models run quantum chemistry 100 times faster, turning hours into minutes. Rotation-aware networks such as Deep HE3 preserve how structures turn in space. They reach speedups up to 10,000 times and can simulate 10,000 atoms. Then, GNoME expanded the map. It predicted 2.2 million crystal structures. Of those, 380,000 were predicted thermodynamically stable and viable for synthesis screening, expanding the stable material catalog by roughly an order of magnitude. That was presented as the equivalent of 8 centuries of accumulated materials knowledge compressed into months. Let that scale land. These are candidates, not jars sitting on shelves. Among them were 52,000 layered compounds, stacked like graphene sheets, with possible superconducting uses. GNoME also identified 528 potential lithium-ion conductors, 25 times the previous pool for solid-state battery research. The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with CivilizationX.